I'm going to try and think about integration of some trig functions, having looked at differentiation of some trig functions last time. And we're going to be just reminding ourselves a little bit of what the differentiation does, how that works, and then trying to see, okay, if we know how the differentiation works, can we make the integration work, which is the reverse process of differentiation? Okay. One thing to note for this video, in the graph that you see on the top right of screen, you'll notice that the units on the x-axis are not in degrees. Okay, they are definitely not in degrees. They are measuring in radians. You don't need to worry about that. It's just the way that the program measures it. Everything will work in degrees as we expect it to. Okay. So let's go from there. So what we found out last time was that if we differentiate sine of x, we end up with cos x. Okay, and we can see from our little graph on the side here that when we take a function that is sine of x and we differentiate it, we find the derivative of it, we get cos of x. Okay, so the green line is what we're starting with. If we differentiate, we get the red line. Okay, now what we also said was that if we differentiate cos with like a number times x, something like this here, then we would get the derivative of the trig function multiplied by the kind of derivative of the bit in the middle. Okay, so if we had, for example, sine of 3x, when I differentiate it, I get 3 cos 3x. Okay, the differential of 3x is 3, so we get 3 cos 3x. Okay, change that back to normal. And we also saw that there's this lovely kind of pattern to differentiating with sine and cosine. So sine differentiates to cos, cos differentiates to negative sine, sine differentiates, or negative sine differentiates to negative cos, which differentiates back to sine. Okay? And all of these, to get around in this circle, all we're doing is differentiating. Okay? And so what we want to have a think about now is, well, if we know how to differentiate, do we know how to integrate? And the short answer to that is yes, we do. Now, if we remember that when we integrate a normal expression, say like x cubed, just like that, if I were to integrate that, we would normally raise the power by 1, divide by the new power. Okay? So raising the power by 1 would give us x to the power of 4. Dividing by the new power would give us dividing by 4. And we'd have this constant of integration added on. Okay? And that's because if we were to differentiate this thing, we would end up back where we started. Okay? So if I were to find d by dx of x to the power of 4 over 4 plus some number, I would get x cubed. 4 would come down to the front. 4 divided by 4 is 1. The power decreases by 1. And numbers get eliminated when we differentiate. Okay? Constant terms, I should say, not just numbers. Constant terms get eliminated. So we want to see, can we use the fact that differentiation is the reverse of integration to figure out what happens when we integrate sine and cosine? Okay. And the easiest way to start off with this is to look at is to think about cos. Okay. If I were to try and think about what is the integral of cos x, what I would have to think about is what would I have to differentiate to give me cos x? Okay. So what differentiates to give cos x? Well, if we look at our little wheel from earlier, which, hang on a second. We look at our little wheel of knowledge from earlier, what differentiates to give cos x? Well, that's sine x. Okay. So when we integrate cos x, what we're actually going to get is sine x plus our constant of integration. And that is because if we were to differentiate sine x plus c, we would get cos x. Okay? And we could essentially now add a little bit more to our diagram that says, well, if we want to go the other way, so going from cos to sine, rather than differentiating, we would integrate. Okay? So we could say that to go from cos to sine, we would have to integrate. And sometimes we will have to compensate for things which are missing. For example, if we were to say, what is the integral of negative sine x? Well, the integral of negative sine x, take us back this way. Okay, we're going to get cos x plus our constant of integration. Now, if we want to kind of think a little bit, a little bit more in depth into this, we could say that the integral of negative sine x is equal to negative the integral of sine x. Just taken almost a factor of -1 outside of that integral. Now, the integral of sine x, okay, if I've got this, in here, this would simplify to give me cos x, and then I'd have subtract c. Now, the fact that here I've got plus c and here I've got subtract c doesn't really matter. It just means that the numbers that we get for our constants of integration will be of opposite sign. Okay. So, a short little takeaway from what we've got so far is that sine x will differentiate to cos x, so cos x will integrate to become sine x. We want to go clockwise round our little pattern here, then we're differentiating, anti-clockwise, we are integrating. Okay? But one thing which we haven't thought about yet is that we've thought about this. What we've not done is thought about this. Okay? Now, what we have here is we need to think carefully about this number. Okay? So let's have our third little example. I want to integrate sine 3x. Okay. Now, to integrate sine 3x, I'm going to have to think, what would I have to differentiate to give me this thing? Well, to differentiate to get sine, I would have to have negative cos. Okay, you can't quite see that. Here we go. So to differentiate to get sine, I would have to have negative cos. So that's one thing. So I'm going to have negative cos 3x. But hang on, that doesn't quite work either, because if I differentiate negative cos 3x, I would get 3 sine 3x, not sine 3x. Okay? So I need to compensate for the fact that I should have a multiple of 3 here, but I don't. So what I need to do is I need to compensate for that multiple of 3 by doing a division by 3 here. Okay? So I want to compensate for the multiple by 3 by dividing by 3. Okay? So just to finish off down here, so instead of using negative cos 3x, okay, what I'm going to use instead is use negative 1/3 cos 3x. Okay, so just to check, d by dx of negative 1/3 cos 3x. When we're differentiating, the number inside of the differential of the bracket comes out to the front. So I'd have 1/3 times 3, which is 1. So that gets rid of the numbers on the outside. Negative cos differentiates to become sine. So we're going to have 3 times 1/3 sine 3x, which is just sine 3x. Okay, so this thing in here, that is our answer. Now, we don't want to have to go through doing all of that every time we want to integrate a trig function. That's just silly. We instead need to think, right, how can I quickly make a link from here to here? Okay. Well, the first thing is to notice what happens with the trig function. Okay, sine integrates to negative cos, okay, from our little pattern. Okay, sine integrates to give negative cos. Okay, and in differentiating, we would normally multiply by the derivative of the bracket. So in integration, where we divide by things instead of multiplying by things, we divide by that derivative of the inside bracket. Okay. So for the differentiating, we would normally multiply by the derivative of the inside bracket. For integrating, we're going to divide by the derivative of that inside bracket. Okay. So thinking about our little summary up here, we now have that the integral of sine x is negative cos x. And we also have, plus c. Don't forget that constant of integration. Okay? And also that the integral of, let's say, cos kx is equal to 1 over k sine kx plus our constant of integration. Okay? Now, there are lots of proofs that you can use that show you that sine will differentiate to give cos, and so the integration is the reverse of this. At the moment, we can look to kind of take this as face value, or as for what we've shown it here. If you want to, you could look to use differentiation from first principles to connect the two things together, which is quite a good exercise to try and do. But in order to do that, I think you'll need some angle formulae, which I don't believe you've been, if you're in year 12 at least, you wouldn't have seen yet. And if you're in year 13, you should have seen. Okay? So let's try a couple of quick questions just to see how we are doing. So let's do the integral of negative sine 2x. Let's do the integral with respect to x. Let's do the integral of negative cos x dx. Let's do the integral of cos 3x plus 2 dx. And let's have a go at the integral of negative cos 3x plus 2 dx. Okay. So let's have a go at those quick questions. Let's give ourselves, 5 or 6 minutes to have a go at these? We'll go for 5 and then see how we do from there. See if I think that's the information that we need for those. And if you have any questions and you're watching the video live, feel free to type in the questions that you have and I'll answer them as we go. I was muted the whole time. That's annoying. Okay, so basic things to come out of this were that you could see some of the integrals changing up on the screen. You could see and the answers being written out down here. And yeah, when we had this one, the 2 is outside of the cos bracket, but it's contained before the dx, so we knew that we did have to integrate that 2 to become 2x. Okay. This one, we need to differentiate that whole bracket to divide by. Well, the derivative of 3x plus 2 is just 3. So we get negative 1/3 sine 3x plus 2 plus our constant of integration. And don't forget that constant of integration. Okay? It is important to keep in there because it will affect, as we've seen on here, how high up or low down your integral should actually go. Okay. Definite integration, where you've got limits, it works the same way as when you do definite integration in year 12 or for AS maths. With these, you're just making sure that you put your value of x in where you have x's in your expressions. Okay? And yeah, that pretty much kind of sums up some of the stuff that you'll do with integration of trig functions as well. Okay? Having this will help you, but the more that you kind of get fluent with differentiating and integrating your trig functions, the better. It does come up an awful lot in terms of mechanics, in terms of some pure maths as well. Anything that involves some kind of back and fro movement, we can express its position in terms of cosine and sine. Sound waves are a combination of sine and cosine. So being able to differentiate and integrate with these, really important. Okay. If you are one of my classes, as always, you can feel free to email me any questions that you have based upon these videos. If you want the practice, you can find some really good exercises in the old Solomon papers and Solomon worksheets, which you can find on Physics and Maths Tutor. And yeah, and you can always use the textbooks to practice these things as well. Okay. So that is a little summary on integrating with trig functions. I'll leave it there. I'm going to say ta-ra.